This lecture is part of a series of lectures on modular forms and will be more about theta functions. So last lecture we covered theta functions in one dimension, and now I'm going to look at theta functions in higher dimensions. So the one-dimensional theta function looked like this, where you sum over all integers of e to the pi I m squared tau. And we saw this was sort of more or less a modular form in tau of weight a half. And what we're going to do is replace the integers by a lattice L in some n-dimensional Euclidean space. So you recall that a lattice L is essentially just a free abelian group, and you probably want the inner products of elements to be integers and things like that, but whatever. So we define the theta function of a lattice L just by summing over all elements of the lattice L, and we sum over e to the pi I times tau times the norm of the element of the lattice. So when L is the integers in R1, this is just the theta function we described last time. And there are some obvious functional equations this satisfies. First of all, theta L of tau plus 2 is equal to theta L of tau, provided the norm of any element of the lattice, that's the square of its length, is an integer. Well, we can get this invariance under tau plus 2 down to tau plus 1, so theta L of tau plus 1 is equal to theta L of tau, provided the norm of any vector in the lattice is even. Now we want to discuss what happens if we change tau to minus 1 over tau. And in the one-dimensional case, we use the Poisson summation formula. So in the n-dimensional case, we're again going to use the Poisson summation formula. So what does it say? Well, it says that if you sum over all x inside some lattice of f of x, this is equal to some constant times the sum over all y in the dual lattice of the Fourier transform at the point y. So the dual lattice is the set of y such that y has inner product with such the inner product of y with x as an integer whenever x is in the lattice. This constant is something to do with 1 over the volume of a fundamental domain. And the Fourier transform is, of course, defined. The Fourier transform of y is just the integral over r to the n of e to the pi I, 2 pi I times the inner product of x and y times f of x over d to the n x. So, as usual, you have to remember to put the pi's in the exponent rather than in front of the integral sign in order to get neat results. So what we do is we just apply the Poisson summation formula to the function where f of x is equal to e to the I pi times the norm of x times tau. And the Fourier transform is going to be a similar expression, except tau changes to minus 1 over tau, and you put a constant in front of it, which I won't write down because if I do I'll get it wrong. And you find that the theta function of L of minus 1 over tau is just equal to tau over I to the n over 2 times 1 over some volume of a fundamental domain times the theta function of the dual lattice at tau. So this is slightly different from the one-dimensional case because we go from a lattice theta function of a lattice L to the theta function of its dual lattice if we change tau to minus 1 over tau. In the one-dimensional case, z is its own dual, so we didn't have this problem. Now let's look at a special case of this. Suppose that first L is equal to its dual. And secondly, suppose that L is even. This means that the norm of any element of the lattice is an even integer. Then we find that theta of tau plus 1 is equal to theta of tau, and we also find that theta of minus 1 over tau is equal to tau over I the n over 2 times theta of tau. So we've got transformations under tau plus 1 and minus 1 over tau. So we get transformations under all elements of SL2 over the integers. And these are just like the usual transformation formulas we define for level 1 modular form, except we've got this funny factor of 1 over I to the n over 2. And we'll talk about that a little bit more later. So the question is, can we find any lattices that are equal to their own duals and are also even? So if we miss out the condition that the lattice is even, this is easy because we just take the obvious lattice z to the n, which is self-dual. Well, we can find an example of this, which is the famous E8 lattice. So here, what we do is we take all vectors n1 up to n8, and if we took all these ni's to be integers, this would be self-dual, but it wouldn't quite be even. So to make it even, we add the conditions that the sum of the ni is even. And that obviously means the norm of every vector is even. But the trouble is it's no longer self-dual because we've discarded half these vectors. So what we do is we add back in the same number of vectors. So we take the vectors such that all ni are integers, or all the ni are integers plus a half. So we've sort of thrown away half the vectors of the lattice, but we've then added an equal number of other vectors. And you can easily check that this lattice is now self-dual. So E8 is E8 dual. And also all vectors have even norm. For example, if you take the vector consisting of all the halves, then this is norm 8 times a half squared, which is equal to 2, which is even. And similarly, you can check that if all the coordinates are integers plus a half, then the norm is still going to be some sort of even integer. So this works provided 8 divides the dimension. So we can in fact do this in any dimension divisible by 8, and we can get lattices E16 and E24 and so on. This lattice is particularly famous because it's the root lattice of the E8 Lie algebra, which is the largest of the exceptional simple Lie algebras. And let's look at what its theta function looks like. Well, we know theta of tau plus 1 is equal to theta of tau because the lattice is even, and theta of minus 1 over tau is equal to tau over I to the 8 times theta tau. Sorry, tau over I to the 4, because we have to divide the exponent by 2, which is equal to tau to the 4 theta tau. And now this irritating factor of I in the functional equation actually cancels out, and you can see this cancels out whenever the dimension is divisible by 8. So theta is a modular form of level 1 and weight 4 for SL2 of z. Well, the space of modular forms of level 1 and weight 4 is just one-dimensional. So the theta function of the E8 lattice is just the Eisenstein series E4. By the way, one of the most annoying notational glitches in mathematics is the fact that the theta function of the E8 lattice is the E4 Eisenstein series, not the E8 Eisenstein series, but it's too late to change notation. You just have to put up with this. So this is equal to 1 plus 240 times sum of sigma 3 of n times q to the n, which is equal to 1 plus 240q plus 2160q squared, and so on. So what we're going to do now is just check this explicitly. We're going to find all the vectors of the E8 lattice of norm 2 and 4 and check that we do actually get these numbers. So let's look at the vectors of norm 2. Well, there are two sorts of vectors. First of all, we can have some vectors with 2 entries that are plus or minus 1 and noughts elsewhere. and the number of these is 8, choose 2, because there are 2 places to choose the ones, and we have to multiply by 2 squared because of the signs, so we get 112 of these. Next we can have plus or minus a half in every coordinate entry. What's happened there? Plus or minus a half. And the number of these is 2 to the 8 divided by 2. And so we've got 2 to the 8 choices of signs, but then we've got to divide by 2 because the sum of all the entries has to be even. So this gives us 128. And if we add these up, we get 240. So we do indeed get 240 norm 2 vectors. So you see this funny number 240 that originally came from Bernoulli numbers is in fact the number of shortest vectors of the E8 Lie algebra root lattice. By the way, this is very closely connected with the dimension of the E8 Lie algebra. So the dimension of the E8 Lie algebra is 248, which is 240, the number of norm 2 vectors, plus the dimension of the root lattice, which is 8. So this actually also calculates the dimension of the E8 Lie algebra. Now let's just do the vectors with norm 4. So here we have 4 entries that are plus or minus 1, and the number of these is 8, choose 4 times 2 to the 4, and 8 choose 4 is times 2 to the 4 is 1120, and then we have plus or minus 3 over 2, plus or minus a half, plus or minus a half, and the number of these is, well, we've got 8 choices of signs, and then we've got 8 places where we can put the entry 3 over 2, but then we have to divide by 2 because the sum of the entries has to be even, and this gives us 1024, and if we add these up we get 1144, so we get 2144, which is a little bit less than the number we ought to have got. So we've obviously missed out some vectors, and in fact we've missed out the vectors which have a single entry that's plus or minus 2, and the number of these is 8 times 2, which is 16, and if we add these all up we should get 2160. So we do indeed get the number of norm 4 vectors predicted by modular form theory. Now I'll give a few more applications of this. So there's a famous problem. Can you hear the shape of a drum? So what this means is you take a Riemannian metric and you look at the eigenvalues of the Laplace operator on it. Well, never mind what that means, because all we're going to do is we're going to take M to be a special manifold of the form R to the n modulo a lattice, and then the eigenvalues of the Laplacian correspond to the norms of vectors of L. And of course we count the eigenvalues with their multiplicities. So we want to know, can you find 2 lattices which have the same number of vectors of any given norm, in other words, the same theta function. And Milner pointed out that you can do this very easily. You take the lattice E8 squared, the sum of 2 copies of the E8 lattice, and we can take the E16 lattice, which is the analogue of the E8 lattice in 16 dimensions. Now the theta function of either of these is a modular form of weight 8, and the space of modular forms of weight 8 is just one-dimensional, so it must be the Eisenstein series E8, not the lattice E8, of course. So we've got 2 lattices with the same theta function, so the drums made out of these would sound the same. Well, of course you need to check that these are actually different manifolds, different Riemannian manifolds, and you notice that here the norm 2 vectors can be split into 2 orthogonal subsets, non-empty orthogonal subsets, whereas you can easily check that for the E16 lattice you can't do this. So these really are different lattices and they give you different Riemannian manifolds, but they have the same spectrum, so if you had these 16-dimensional drums they would sound exactly the same. So next application, we can ask how many length root 4 vectors are there in the Leech lattice? And what we know about the Leech lattice is it's even, unimodular, that means self-dual, 24 dimensions, and it has no vectors of length root 2. And I want to calculate the number of vectors of length root 4 in this lattice with just this information. And at first sight, you don't seem to have enough information to do this. All I've told you is a few random facts about the lattice, and for all you know, there are lots and lots of lattices with this property, and maybe they have lots of different numbers of vectors of length root 4. And in high dimensions, you'd get lots and lots of lattices, and they may have different numbers of root 4 vectors. However, in 24 dimensions, we can actually pin down the number of root 4 vectors using the theory of modular forms. So the theta function is going to be a modular form of weight 12. And now the space of modular forms of weight 12 is 2-dimensional, and it's spanned by, say, E4 cubed and the discriminant delta. And now the coefficient of q to the 0 must be equal to 1 because there's just one vector of norm 0. And the coefficient of q to the 1 must be 0 because we've said there are no vectors of length root 2. And so this uniquely determines its theta function because it must lie in a 2-dimensional space, and we found 2 linear conditions on it. So the theta function of the Leech lattice must be, well, we take E4 cubed to get it to have constant term 1, and then we subtract 720 copies of delta. So you remember delta is equal to q plus something or other, and E4 cubed will be equal to 720q, 1 plus 720q, and so on. So this will now have theta series 1 plus 0 times q, and you can now work out the coefficient of q squared, and it's 196560. So we've sort of magically found the number of norm 4 vectors of the Leech lattice, knowing almost nothing about the Leech lattice. So if you want an exercise, you can do the same thing in 32 dimensions. There are more than 10 million such lattices with no vectors of length root 2, as Oliver King proved, and the problem is to work out how many vectors of length root 4 does such a lattice have. Well, we were asking whether there were any even self-dual lattices, and we found one in dimension 8, and you can obviously ask, why did we have to go all the way up to 8? So can we find an even self-dual lattice in dimension less than 8? And of course the dimension should be greater than 0 because the 0-dimensional lattice is even and self-dual. And the answer is you can't. The dimension is always divisible by 8. And we can prove this using modular forms as follows. If not, we can, and we've got a lattice L, then we can take L plus L, or L plus L plus L plus L to get the dimension congruent to 4 modulo 8. So if it is dimension 3, for example, we take a sum of 4 copies of it and we would get a lattice that is dimension 12, which is 4 mod 8. So we just need to prove you can't have the dimension divisible by 4 modulo 8. And to do this, we notice that the theta function of the lattice satisfies theta of a tau plus b over c tau plus d is equal to chi of a, b, c, d times c tau plus d to the n over 2, where n is the dimension, times theta of tau, where chi is a certain character of an element of SL2. So chi of a, b must be chi of a times chi of b. And we know what chi is for two matrices. First of all, chi for the matrix 1, 1, 0, 1 must be plus 1 because theta is invariant under tau goes to tau plus 1. Secondly, we know that chi of the matrix 1, minus 1, 1, 0 must be equal to minus 1. And that's because we know the theta function satisfies theta of minus 1 over tau is equal to tau over I to the n over 2 times theta of tau. And here we're getting a factor of minus I to the n over 2, which is equal to minus 1 because n is congruent to 4 modulo 8. Well, we can now reach a contradiction. So I'm going to call this element 1101t, and the element 0, minus 1, 1, 0, I'm going to call s. So chi is a character that takes t to 1 and it takes s to minus 1. Well, we notice that st cubed is equal to 1 in PSL2 of z. So it's either plus or minus 1 in SL2 of z, depending on which sign convention you use for s. So chi of st cubed must be equal to plus 1. However, this contradicts the fact that chi of t is 1 and chi of s is minus 1. So we reach a contradiction if we assume that the dimension of L is 4 modulo 8. So this proves that any even self-dual lattice must have dimension divisible by 8. This is just one example of the fact that the dimensions 8 and 24 are very special in the theory of modular forms. So here we've shown that 8 appears because it's the smallest possible dimension of an even self-dual lattice. 24 appears because it's the smallest dimension of an even self-dual lattice with no roots. You can see we've just shown that dimension of such a lattice must be divisible by 8, and it can't have dimension 8 or 16 because we calculated the theta functions of such lattices and they all have vectors of length root 2. Okay, so next lecture we will probably be discussing Hecker operators.